أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will discuss the optical properties. Actually we have discussed the optical property in the earlier class as well, but for detailed understanding we included some new topic relevant to the optical property and the detailed study of optical property. So this lecture is also devoted to the understanding the concept of optical property. So basically, when some electromagnetic radiations interact with matters, so there are four different possibilities. The first one is the absorption. That is actually the absorption process where photon is absorbed, and that is utilized in shifting an electron from the valence band toward the conduction band. This is the first case, and in this case we look at the number of absorbed photon intensity versus the photon frequency. The second possibility is that the upcoming radiation might be reflected depending on the energy. So this is the reflection process, and in this case we look toward the reflected photon, and in that case if we want to draw the curve for that, we need to draw a curve between the reflected photon versus the photon frequency. The other possibility is that the upcoming radiation pass through the material, and this is actually called as the transmission process, or the beam is called as the transmitted beam. So in this case, if you want to depict the data in the form of curve, so that is actually we need to draw the transmitted photon intensity versus the photon frequencies. And the final other possibility is the emission process, that we want to look at the emitted photon intensity versus the photon frequency. I mean the radiation which is absorbed, so the electron cannot remain for longer time in the conduction band, so it will lead to the emission process. So that is, we need to look toward the emitted photon versus the photon frequency. So how we can develop the curves or the spectra for the absorption, reflection and transmission and even the emission process. So how we can develop it? For this thing, what we need a complicated a detailed study of these things, the interaction between the matter and the upcoming radiations. So for that thing we need to know about the band structure, the energy gap, the band gap, that is actually the distance between the valence band maximum and the conduction band minimum, the effects in solid, some vibrational property, and all relevant properties to the optical properties. So how light interact with bulk materials? So we already discussed in the earlier lectures, earlier slide, but this is actually the detailed depiction of the data. All the possibility are depicted in the form of rays. So we have a material that is semi-transparent material, so light is incident upon it. So the possibility are the refraction, transmission, reflection. Reflection is further divided into three categories. It might be a specular reflection, we discussed earlier. It might be total internal reflection, that is used in some special things just like optical fibers, or we have diffuse reflection, that is the diffuse reflection. And the other possibility is the scattering, and in scattering we have the dispersion also, where the different wavelengths bend and we form a spectrum is formed. So how we can discuss the interaction between the photons and the matters? But for understanding this thing, the most important thing to us is that we need to know what is photon actually. So there are different ideas about the nature of photon, and the first thing where some of the scientists initially considered that light as actually has a wave nature, and some of the scientists just like Newton, they considered that light has a particle natures. So we have two scientists over here, just like the Isaac Newton and the Huygens. where they considered that the waves, the radiation have a particle nature and wave nature respectively. So both of them strongly disagree with each other. Later on in the next slide we will show how we have a dual nature of matter. So there was further development in science, where in 1905 Einstein developed a data regarding the wave and particle properties of light, and that was made by some development or some experiment. This experiment was some of the experiment was just like photoelectric effect, where it was considered that the waves, I mean there was some change in the it was considered that light has a quantized nature, and that was given the name of photon. So later on the scientists agree after the de Broglie hypothesis, the scientists agree that the waves has both particle nature, I mean the radiation has both particle nature and wave nature. So and both the natures are relevant, I mean related to each other. I means whenever any particle is moving, a wave is associated with that, and we can find out the wavelength of that wave from that particular equation, and hc is equal to hc divided by lambda. So that particular quantized nature of light was given as the name of photon, and I mean so we have a dual nature for the radiation, wave nature and a particle nature, and the discrete, I mean the quantized nature of that particle, what we consider for the light is made of, is the photon. So light is emitted in multiple of certain minimum energy unit that are actually called as photon. So how an electron can be emitted if light is shine on a metal? The energy of light is not spread but propagate like particles. So how we can calculate, discuss the photon? So photon is actually when we are dealing with events at atomic scale, it is often based to regard light is composed of quasi-particle. So photon is actually quanta of light or quantum of light. So its electromagnetic radiations are composed of photons, and we can calculate the energy of photon, that is actually is equal to h nav or is equal to hc divided by lambda. So if there is a particle that is in state of motion, so we can find out the wavelength associated with the particle, and that could be obtained from the equation is equal to hc divided by lambda, where lambda is associated there. So it means if the particle are moving with very high speed and have smaller mass, then we can get this appreciable amount, I means we can deduct this wavelength. So light as an electromagnetic wave, that is actually the wave nature of matter, how it is developed. So light as an electromagnetic wave is characterized by a combination of a time-varying electric field and time-varying magnetic field H propagating through the space. So from the Maxwell equation, it was found that light has a wave nature. So it gives that E and H satisfy the same waves equation. So this is something about the Maxwell equations. So the speed of light is represented by c, and its value is 3 multiplied by 8 3 multiplied by 8 3 multiplied by 10 10 to the power 8 meter per second. So we can calculate this from a very simple equation, that is c is equal to 1 over epsilon naught mu naught, where epsilon naught and mu naught are the electric permeability and magnetic permeability respectively. So from this we can get the value of c. Actually c is if we consider the refractive index, that is the ratio between the motion of that particular wave in the medium and in the space. So from that equation we can get the value of v, and v is equal to c divided by n, v is equal to nu lambda, and in that we can calculate the unknown values and find out the speed of light. So the speed of light in a medium is related to the electric and magnetic properties of the medium. So the speed of light in vacuum can be expressed in this equation, that is c is equal to 1 over mu naught epsilon naught under the root. So this is electromagnetic spectrum, which is consists of a wide range of wavelengths or frequencies, starting from gamma rays and ending at radio wave, not ending but it's extended towards radio waves. We have different electromagnetic waves that are different from each other based on their wavelength and frequency. Light is also a part of electromagnetic radiation and is lying in the range of 400 to 700 nanometer. So we have different light color that are available in it, just like violet, blue, green, yellow, orange and red. So how we can observe the visible light? Visible light, as we discussed, that comes in the range of 400 to 700 nanometer approximately. So if the visible light is created by a semiconductor material, it means that the band gap should be equal to or around about 3.1 to 1.8 electron volt, because we already discussed that when if you want to shift an electron from the valence band of a semiconductor toward the conduction band of a semiconductor, the photon needed for this purpose should be its energy should be equal to the difference between the two energy levels. So we can detect, our eyes can detect the visible light, and that is created in such a manner. So if there is visual appearance, I mean for the insulator, metal and semiconductor material, appearance or color depends on the interaction between the light with the electron configuration in the metal. So there are different type of materials. Some are transparent, some are opaque, and some are partially transparent. So it depends upon their band structure and different optical property of that particular semiconductor or insulating materials. So this is the distribution of visible light among the spectrum. We have violet and violet, indigo, blue, green, yellow and red colors that are present here. So in order to create or to produce a particular sort of light, we need a semiconductor with this relevant band gap, and the band gap could be easily calculated divided by, from the equation that is equal to hc divided by lambda. In that, the wavelength and the band gap are related with each other. So even we discussed the Lombard law in the last equation, that we have different possibility, and even on the first slide we discussed the different possibility for the light, that are the reflection, refraction, transmission and scattering process. So that depends upon the band gap of that material, and why some material are transparent, it also depends upon, just like we have glass that is as an insulator having a huge band gap, so it is difficult for electron to jump across the band gap, so there is no absorption. So what happen, E cap is greater than 5 electron volt, or even greater than, for visible light the band gap is 2.7 to 1.6 nanometer. So all color photon are transmitted with no absorption, hence the light is transmitted and the material is transparent. So this is something from the well known equation. So this is the absorption spectrum for the material. What type of radiation will be absorbed by semiconductor material, and in which range, or what type of peak will be created. Different phenomena are responsible for the absorption process. In some cases, the electron migration from the valence band to conduction band are possible for that. In some cases, the core electron, depending on the energy of the upcoming photon, in some cases there is the vibration of the electron are responsible for that. In some cases, band absorption are responsible for the light, because the energy of that light or upcoming radiation is very low, so it can only occur the interband transition. Even it's also possible that the transition between the impurity states and the band gap and the band where the valence or conduction band occurs. So this is actually we have inter and intra-band transition. So depending on that, so we have different peak for different things. Just like we have a peak that is actually the peak between valence to conduction band transitions. This is a big peak. A broad peak is showing the valence to valence band, the transition of electron between valence and conduction band. This is transition is due to free exciton, Here we have bond exciton transition, I mean that is we have free carrier absorption and we have phonon bands. So free carrier absorption and impurity absorption is responsible for such peak. So each of the peak is responsible for some physical activity where the electron is accelerated, moved from one place to another place, or disturbed at its position. So this is actually the extended study, optical study of the semiconductor. But in general, as we are at this level, you are the BS and MSc student. So at this level, the most important thing for you to understand is that we need to know that each of the peak is relevant to a particular physical property which is responsible for the absorption of that photon and the creation of some activity inside their particular material. So this is the absorption spectra of semiconductor materials. So the absorption process, how it occurs. The absorption process is an important phenomena in the description of the optical property of the semiconductor material, because it is actually the basic process from where we can extend all other property. Because if light is not absorbed, definitely it will be a type of transmitted. So absorption is the most important process, especially if we use the semiconductor material for photoelectrochemical application. So absorption is the most important process, because in that case the optical photon or the visible photon are absorbed, creating electron hole pairs, and that whole electron hole pairs or the pair of charges are utilized for oxidation and reduction processes. The same technology is used in water splitting, where water is converted into oxygen and hydrogen is used as an energy source for. So this is actually the absorption is the most important process, where it is started and the electron hole pairs are generated, and that can be further utilized in different processes, or in the next parallel process might come back. The electron might come back to its valence band, creating or generating another photon that's whose energy is equal to the difference between the energy levels. So the photon electron interaction process obviously depends strongly on the photon energy. I mean, this is very important for us. If its energy is only the material can see the photon and energy, and based on that energy the photon might be absorbed, scattered, transmitted, or transmitted. So we have lower energy photon that interact principally by ionization or excitation of the solid valence electrons. We have low energy photon, whose energy is less than 10 electron volt, or in the infrared range of visible or ultraviolet light in the electromagnetic spectrum. In some cases, high energy photon whose energy is greater than 4 electron volt are in X-rays and gamma rays region of the electromagnetic spectrum. So the minimum photon energy to excite or ionize the solid and the valence electron is actually the ionized electron is this one, and this is actually the minimum amount of energy required for that purpose is called as the absorption age or absorption threshold. So there is absorption threshold for different type of semiconductor material, and that absorption threshold or absorption age shows the minimum amount of energy that the photon carry to excite or ionize the solid valence electron and move it towards the conduction band. So this is the minimum amount of that particular energy. So we have this is valence band and conduction band transition, valence band to conduction band transition of electron. This is actually called as band to band transition. When a photon having energy equal to the difference between the energy levels falls on it, so as a result of that, charge pairs are created. An electron is migrated from valence band toward the conduction band, and a hole is created inside the valence band. So these charge pairs are further utilized in different processes. So this is a simple process of electron hole pair generation. So here in this case we say the minimum criteria for electron hole pair generation is that the energy of upcoming photon should be equal to the difference between the energy level, or in other words, in very simple word, the energy of that upcoming photon should be equal to the band gap energy. So we have different type, but depending on the nature of band gap, we have different type of bands. It might be we have direct band gap and we have indirect band gap. So some of the semiconductor carry direct band gap and some of the semiconductor have indirect band gap. Indirect band gap, the maximum of valence band and the minimum of conduction band lies at the same value of k. Here in this case we see this is the wave vector k. This is the at horizontal axis we have k, and at the vertical axis we have energy. So this the maximum of valence band and the conduction of maximum of valence band and the minimum of conduction band lies at the same value of k. This such semiconductor material called as indirect band gap, and the transition in this case is very simple. In some cases we have indirect band gap semiconductor. In that case the maximum of valence band and the minimum of conduction band lies at the different value of k. So this is not actually a direct transition, but that is an indirect transition where the electron is moved from valence band toward the conduction band with the help of some impurity level, or some state is created which is responsible, or that is actually an indirect transition of electron from the valence band toward the conduction band. So it is a bit complicated compared to the direct band transition. So this is an example of indirect band gap transition. Indirect band gap semiconductor transition, where an electron is shifted from the valence band toward the conduction band with the help of an impurity level or defect level that is created in the band gap. Because direct transition in this case is not possible, because both the maximum of conduction band and minimum of the valence band maximum of the valence band and minimum of the conduction band lies at the different value of k. So we have the simple process where the absorption occurs, the electron hole pairs are generated and the photon is absorbed, leading to the creation of electron, and that electron is migrated from valence band toward the conduction band. This is a simple case, and we can change the optical absorption threshold of many semiconductor material by doping, and that doping create an isolated states, impurity states, either above the valence band maximum or below the conduction band minimum. So photoconductivity is also a phenomena that is relevant to the photon absorption, and that improves the conductivity of semiconductor material. So in this case, charge carrier that are electron and holes that are created in the corresponding bands by absorption of light, and that absorption of light can increase the number of photons and the number of electron in the valence conduction band and number of holes in the valence band, leading toward the improvement or increase current in that particular semiconductor material. So this is something about the understanding of the optical properties in detail. Thank you very much for now.